Good evening friends. I hope you are following the thermodynamic video lectures thoroughly. Today our goal is to learn about the Carnot engine. Let we start our syllabus. Carnot engine. So Carnot engine is a theoretical engine. It is a theoretical engine. And also the working substance in this heat engine is it has a ideal gas, it has an ideal gas as working substance. In this heat engine, working substance is ideal gas, and also it is free from the all defects. It is free from all defects. It is free from all defects. The each and every process in the heat engine, Carnot engine, are the reversible process. So each process in Carnot engine is reversible process. That engine can be called it as a Carnot engine. That means a engine which is the Carnot engine is a theoretical engine, and also which is having the working substance is the ideal gas, and it has the free from the all defects as compared to the other heat engine, and also each process of the Carnot engine can be reversible. That engine can be called it as a Carnot engine. Now let me go to the parts in the parts of Carnot engine. Parts of Carnot engine we are discussing here. So the parts of Carnot engine is the first part we are going to discuss, that is the source. So source is nothing but it is the heat reservoir point. It is a heat reservoir point. It is a heat reservoir point, and also it is having at larger temperature. It has at larger temperature point, and also it has the larger temperature at generally we will take it as a T1 temperature, and also it has higher larger thermal capacity. It has higher thermal capacity. Higher thermal capacity. What does that mean by higher thermal capacity? That means if some amount of heat energy is taken from this part, then there is no any temperature change in this part, and also it can supply constant amount of heat per cycle to working substance. That is the very important. So it can supply constant amount of heat per cycle to working substance. That is named as a source. So generally we will take it as a one part here. So it will having higher temperature and also higher thermal capacity. If these can be send some amount of heat to the working substance, generally we will take it as a Q1. So due to sending this amount of heat energy, the temperature of this source may not be vary. That is called it as a source. Now let me go to the insulating cylinder. Another part is the insulating cylinder. So what does that mean by insulating cylinder? So it is a cylinder which having the all sides of the walls of the cylinder is perfectly insulated. That is the insulating cylinder. it is a perfectly insulating walls cylinder. So this cylinder is consisting of a frictionless movable insulating piston. So it consists of perfectly insulating frictional movable frictional less frictionless piston. So it will consisting of perfectly insulating movable frictionless piston. So this is having, and also only the bottom side of the cylinder can only the bottom side of the cylinder is perfectly it is a perfectly conducting wall. So it is a perfectly conducting wall. Let me take, this is the cylinder. So the cylinder which is having this one, this is the all sides of the walls are the perfectly insulating walls, and also the piston is also be perfectly insulating walls. So these sides of the walls of the cylinders, the piston is a frictionless piston, and only the bottom side of the cylinder is a perfectly conducting wall. That means it can allow the heat energy from the working substance and working substance to the surrounding. This is the important point of the insulating cylinder. Let me go to the another one. So working substance. So what does it mean by working substance? In the Carnot heat engine, the working substance is the perfectly ideal gas. So it is an ideal gas. We will use an ideal gas is the working substance in the Carnot heat engine. So now what does it mean by sink? Let me go to the sink. So what does it mean by sink? This is also the heat reservoir which is having at lower temperature. It is a heat reservoir. It is at lower temperature. So the temperature is generally denoted with the T2, lower temperature. This temperature is generally denoted with the T2. So it is ready to absorb heat energy which is sending from the working substance. It can absorb heat energy which is received from working substance. So working substance, from the working substance the heat energy can be absorbed. So this is ready to absorb the heat energy from the working substance. So now as the absorption of heat energy from the heat energy which is received from the working substance, then the temperature of this sink may not be changes, because of it is having the higher thermal conductivity. So higher thermal conductivity. So that's why it is having the because of due to this higher thermal capacity, the temperature may not be varies. So due to higher thermal capacity, of sink, its temperature will constant. The temperature will be constant, so the temperature will be constant due to even it is absorbing the some heat energy from the working substance, so its temperature is constant. So other part is the insulating stand. So this is also for one part is there. The insulating stand is used to hold the cylinder. So when we required, if you want to block the bottom side of the cylinder without any exchange of heat energy, it will useful to hold the cylinder. So that means it is a purely it is nothing but it is a purely insulating stand. Insulating part means it is it cannot allow, because that means that is it should not allow any heat from this part. That means it won't exchange the heat energy from this part, means it can act as a adiabatic wall. So that means we will call insulating wall. So like when this part is generally, I told that the cylinder is consisting of the all sides of the walls are the adiabatic walls. Only the bottom side of this bottom side of the cylinder is a purely conducting wall. To block this flow of heat energy from the surrounding to cylinder, we need to keep the cylinder on insulating stand. That means this insulating stand is used to block. So if I keep the cylinder on this insulating stand, means they won't allow the heat energy from the surrounding to working substance. This is the importance of the about the Carnot heat engine and its important and its parts. Now let me move on for the what is the Carnot cycle. So Carnot cycle is nothing but when the engine is working, so then the working substance undergoes a cycle is known as the Carnot cycle. That means a Carnot engine is under working, the working substance is undergoes a cycle. That cycle is called as a Carnot cycle. When Carnot engine is working, the working substance undergoes, so the working substance undergoes a cyclic process. A working substance undergoes a cyclic process. Then this process is called Carnot cycle. This process is called the Carnot cycle. So the working substance is going to the a cyclic process. That process is called the Carnot cycle. Otherwise, Carnot cycle, the total Carnot cycle is consisting of four steps or 4 parts. So the total the Carnot cycle, the Carnot consists of 4 parts or steps. 4 parts or 4 steps, and generally we will call it as a stroke. So they will call it as a strokes also. So they will consisting of 4 parts or 4 steps or 4 strokes. How the cyclic process can be drawn means with help of the PV diagram we will draw. So it is the pressure, it is the volume. So this the first step, the Carnot cycle will start the initial P1 and V1 and T1 temperature. It will go to the isothermal expansion process from point A to B. Isothermal expansion process is going. So the P2 V2, as the isothermal expansion is there, that's the temperature is equal to T1 is there. So from B to it is undergoes the adiabatic expansion. So adiabatic expansion, it will go to the up to point C. Again adiabatic expansion means temperature and volume will be changes, temperature will changes T2. So it will send to the isothermal compression like this. So again here the P4 V4 and T2 will be have, because of it is the adiabatic isothermal compression. So again it will send to the to its initial part because with help of the adiabatic compression, from again it will reach to the P1 V1 and T1 part. So it is the C means it is the D. So if we draw a line, perpendicular lines, if we draw a perpendicular line on this volume axis, let me take it up to D is completed, E, F, this part is the G, this part is the H. Now we need to know each and every step in the Carnot cycle. That is the very important. Let me start that one also. So let me start first process we will discuss. So the first process, the first part is the first stage, we can call it as, or stroke we will call it as first stroke, we will call it as a first stroke, first stage or first stroke. Which process it is? So it is already told, it is a isothermal expansion or isothermal expansion. It is the isothermal expansion. Let me draw a graph like this. From a point A to point B, the ideal gas is expanding, that is equal to P1 V1 and temperature T1 to, it is moving to P2 volume V2 to temperature T1 only. When it is going, so it is the isothermal expansion means what is happening here to maintain the at constant temperature means how it possible. So the cylinder, the conducting the cylinder means all side of the cylinder is having conducting walls we are having, adiabatic walls we are having. Only the bottom side of the cylinder having the conducting walls we are having. So the cylinder is contacting with the source. So this is the part of the source we are conducting. So source we are carrying, source is source is at a higher temperature of the temperature T1 temperature we are having. So as the temperature is the T1, so this process which process is expecting in the working substance, that process is purely isothermal process. See, then we are allowing to expand this gas. That means the gas is expanding, then pressure and volume will vary. So the P1 and V1 and it changes to P2 and V2, but the temperature is maintained because of the cylinder bottom surface is contact with the source. Then what is the work done in this process? So let me take this volume is here is the this one we are taking. What is the work done? So what is the point we are taking here? E and G we are taking. So here is the E and G, this is the point B we are taking. So work done in this process is equal to work done in this process is equal to, so then to when the gas is expanding, to maintain that constant temperature of this gas, so it must be absorb some of the heat energy from the source. That is nothing but heat absorbed by the gas by the system. So heat absorbed by the system or by the gas, we will call it as by the system. So what is the work done formula? Work done formula is nothing but initial volume of the V1, final volume of the V2 into P into dV. This formula we are having. So as ideal gas process we are having here, P is also variable. So with help of the ideal gas equation, PV is equal to nRT formula we are having. P is equal to nRT by V we are getting. So the temperature is constant here, that is equal to integral of nR T1 divided by V into delta V we are getting. So nR T1, if we take the common term means, so we will get the log of V we will get. So we need to apply the limits. Then apply the limits here. nR T1 into log of limits we are applying means upper limit is the V2 divided by lower limit is the V1 with help of the base E. This is the working. So as for the general formula, this value is nothing but area enclosed in this PV diagram towards to the volume axis, toward to the volume axis, that is equal to area under ABGE. ABGEA. This is the area under the, sorry, what happened? 1 minute. This is not responding. 1 minute please. Yes, it is working. So this value, the work done is equal to first work done, the first work done is equal to, so area under which is having A, B, F, E and A. This is the value we are having. So A, B, G, E, G, E, A. A, B, G, E, A. This board is not responding quickly. A, B, G, E, A. This is the area under the graph. Now let me go to the second stage. So the second stage we are going. So second stage of this one, or second stage or second stroke, the second stroke of this one, or this process is called it as a adiabatic expansion process. It is an adiabatic expansion. It is an adiabatic expansion graph. So in the previous graph what we discussed means from A to B we are expanded this gas as an isothermal expansion. Now we are moving from this one adiabatic expansion, like this we are moving. So now like this we are moving. This is the adiabatic expansion of gas, somewhat more curved nature we are taking. So this is from B to C we are moving. So as gas is moving from B to C, in the previous stage P2, V2, T1 is there. So as the gas is moving, to move the gas from adiabatic expansion, what we need to do? So in the adiabatic expansion, they should not have any exchange of heat energy from the surrounding to system, and system to surrounding means the cylinder is kept on a insulating stand and allowed to expand. So that means what is we are doing? So the cylinder which is having the working substance of the cylinder, we kept in this. So we kept the cylinder on the insulating part of the insulating stand we kept. Then this bottom surface also is not have the provision to exchange of heat energy from the system to surrounding and surrounding to system. So there is no any provision of heat energy. This part is not having allowing this one. This direction is not allowing. This is the very important. So then what will happen, the process will maintain here adiabatic process while having, and we are allowing to expansion of the cylinder. So the gas is ready to allowing to expansion, that's why this volume is expanding. So then what will happen, it will go move to the another place, the pressure P3 and volume also V3 and temperature also T2. We are observing the temperature is the T2 temperature we are getting. So T2, this is the temperature and pressure and volume and temperature at point C. Then what is the work done in this process, that is the very important. So work done in this process, let me take W2. I am taking W2 is equal to, I already discussed about this work done in the adiabatic process formula. We already discussed what is that process. Integral of P into dV is there, the initial volume of the V2, final volume of the V3 is there. This value we already discussed, R divided by gamma minus 1 into T1 minus T2. This formula we are having. This formula is nothing but area enclosed in this part. So this part area we are taking. So this is equal to, I am taking EFGH we are taking. So this is the B, this is the C. So area enclosed in this part means BHGB. This part we are taking. So area in this part is equal to, okay, it is taking right side. So this is equal to area of BC, what is BCHG formula is there, BCHG, area of BCHG we are getting. So this formula we need to recall, we need to check the previous video links. You can easily identify what is the, how we are derived this formula. So that is equal to W2. In the similar process we are following the in the third stage. So third stage or Stoke, what is this process? It is the isothermal compression process. So isothermal compression process. So to do this isothermal compression process, what we need to do means we need to keep our cylinder so in a sink part, and also we are compressing the cylinder. So that means what I am saying. So the bottom surface of the cylinder is contact with sink, and also we compressed the piston and compressed. So that means we compressed this piston means what will happen. So as we are doing the work on the working substance, then on the system, then temperature will rise. So to maintain the same temperature, the sink is ready to absorb the heat energy. So that means the sink will absorb heat energy. That means we are keeping our cylinder on the at the part of sink. This is the part of the sink. Sink is at a lower temperature of T2. Now we are compressing this piston. So due to this maintain the same constant temperature, some of the heat energy is transferred to the working substance to the sink. That heat energy we are taking the Q2. We are assuming that heat energy is nothing but Q2. So now what is the work done in this process? So how the graph will look like? So the graph will look like in the previous case we arrived from A to B is the isothermal expansion, from B to C is the adiabatic expansion. Now we are moving from C to D is the isothermal compression. So that means So this process C to D, from D to E F, this is the F, this part is nothing but it is G and H, this is the part we are having. So what is this work done in this process? Now work done in this process is equal to work done W3 we are taking. W3 is equal to same formula I am writing. So how much work done is equal to, it is the negative work done, because of we are performing the we are doing the work on the working substance, that's why. So work is nothing but energy only, work and energy both are same. So heat ejected, heat released from the system, to sink, both are same. So this value I am taking is the Q2. What is this value? Integral of P into dV, but we need to keep it as a negative sign. From where to where it is moving? V3 to V4 it is moving. So V3 to V4 we are moving. This negative sign is indicating that it is doing a it is ejecting, this heat energy is ejecting. So now let me check this one from where to where it is moving, that is equal to, what is the formula for this isothermal working process, that is equal to R into what is the temperature in this process? Temperature is the same temperature T2, here is the temperature T1, here is the P3, V3 and T2 is there. Here temperature is equal to P4, V4 and temperature is the T2 only we are having. So now R T2 into log of direct formula I am writing. The direct formula is equal to upper limit value is equal to V4 divided by lower limit value is equal to V3. This negative sign if we send here means R into T2 into log of V3 divided by V4. This negative sign is most important here, because of it is a ejection of heat. In this process heat is ejecting, that is the very important negative process, because we are doing the work on the substance, that's why we need to put the negative work done we need to show. So this is the work done in the W3 or Q2 value is equal to R into log of V3 by V4. Now let me go to the fourth stage or fourth stroke. So the fourth part, so that last part is the fourth stage or fourth stroke, or which process this one? This is the adiabatic compression process. So it is an adiabatic compression process. It is an adiabatic compression process. In this adiabatic compression, how to do adiabatic compression process? So that means there is no any provision of heat exchange between the system and the surrounding. How to do this one? So we need to keep our cylinder on a insulating plate. Then only we will compress the cylinder, then only this adiabatic compression will take its place. So that's why this is the insulating stand. So we are having insulating stand. On the insulating stand we are having, then on this insulating, by keeping this on, we are compressing this cylinder, compressing the piston. Then the temperature will somewhat increases from the lower temperature of this substance. So it will move to the higher temperature up to the compression will take place. The system must be reached to its initial condition. That process only we are compressing the cylinder. So that means if we draw a PV diagram here, this is the P and V. The first process what we did, it is the A to B, it is the isothermal expansion. From B to C, it is the adiabatic expansion. From C to D, it is the isothermal compression. From D to A, we are moving. This is the adiabatic compression. So this part we are taking that this is the E part, this part we are taking, this is the F part. So what is the work done in this process? That is the very important. So the work done in this process is equal to when the compression will takes place, means it is the adiabatic compression, means negative of work done, integral of where to where we are moving, the initial part of this, what is this part, so it is having P4 V4 into T2. So from where we are reaching P1 V1 into T1, we are reaching to its initial condition. So then so we are moving from V4 to V1, we are moving that is equal to P into dV. Again the negative sign we are keeping aside, that what is the process wherein adiabatic process gamma R by gamma minus 1 into T2 minus T1. This is the formula we are getting. Now if we send this negative sign, this one is equal to, so then what we will get, that is equal to R divided by gamma minus 1 into T1 minus T2. These are the formula. That is equal to area under AD, please check this one, ADFEA. This is the area under this graph only. We will get the total work done, or how much amount of work done is done this process. Now we need to learn some of the important points in this one. So this is about only purely theoretical part of this Carnot heat engine. Now we need to learn some of the important points of to crack the to solve the problems in the competitive exam. That is the very important point, is the efficiency of Carnot cycle. Efficiency of the Carnot cycle. This is the very important point. So what does that mean? What is the mathematical importance of the efficiency of the Carnot cycle? Means it will denoted with the neta. So the neta is equal to mathematical formula I am writing. So net work done during a cycle divided by heat input per cycle. So this is the important formula for this one. Net work done means we need to take W is equal to W net, that value is equal to W1 plus W2 plus W3 plus W4 we need to take. But will you please observe this one? Let me go to the graphical representation, you can easily understand. So first part I am taking, so sorry, here I am taking. So will you please look on this one? This is the this area will get the W1, this area is get the W2. Will you please look on this one? This is the W2 we are getting, this is the W2. So this area is the W3, again this area is nothing but W4. So W2 and W4 both are same, but W2 is the positive work done because of gas is expanding, work is done by the system. So W4 is a gas is compressing, that means work is done on the system. So W2 in the magnitude, W2 mac factorial is equal to W4 factorial, both are same, and W2 is equal to negative of W4. Because of W2 is the positive work done, W4 is the negative work done. Then if you add these two, W2 plus W4 is equal to 0, W2 plus W4 is equal to 0, because of W4 is equal to negative of W4. This value must be 0. So now come to this our problem, what will happen? So neta value I am going to learn. So in this one W2 and W4 both will cancel, that is equal to W1. So but W3 is a negative work done, I need to write as a W3 is the negative work done, that is equal to negative 3, because of W3 is the negative of W3, because of that one. So I am taking, because of it is a negative work done. General formula I am writing W1, W2 plus W3, but with help of signs also here I am writing. So W3. So it is a net work done. Again, what is the heat input per cycle? So the heat input per cycle is equal to Q1 heat input we are taking. So heat input is equal to heat input per cycle. Per cycle is equal to Q1. In work also we can write this one, how much work done, that is equal to W1 work done. We are supplying this one, it is the positive work done. Then what is the formula we can write? Neta is equal to W divided by Q1, that is equal to W1 minus W3 divided by W1. If we take LCM, 1 minus W3 divided by W1. This is the formula we are having. But in terms of W1 is nothing but Q1, and also W3 is nothing but Q3. This is the formula we already know, as in the derivation also we used that one. So that is equal to neta is equal to, just I am substituting here, Q1 minus Q3 divided by Q3. I am substituting Q1 I am substituting, that is equal to then 1 minus Q3 divided by Q1 we are getting. So then neta formula also, neta value also we are having. So will you please look on this one, this formula, with help of this formula I am writing one more formula. W1 is nothing but the work done. W is what does so this formula I am writing with help of this formula. So 1 minus W3 is nothing but it is the work done during the third process. What is the work done during the third process? It is the isothermal compression process. Isothermal compression process means R into formula I am writing. So that formula is equal to R into log of T1. Let me check W3 formula. W3 formula I am writing. Sorry, here W2. This is R into T2 into log of V3 by V4 formula we are having. That's only I am writing here. So that formula I mean R into T2 into log of V3 divided by V4 we are having, divided by W1 what we are having, R into T1 into log of V2 divided by V1 we are having. This formula we are having. So then R both are will cancel, 1 minus, here 1 is there, 1 minus is there. Then if we write each and every formula, neta is equal to, I am writing each and every formula, W divided by Q1, that is equal to W1 minus W3 divided by W1, that is equal to 1 minus W3 divided by W1, that is equal to 1 minus Q2 divided by Q1, that is equal to 1 minus T2 into log of V3 divided by V4 divided by T1 into log of V2 divided by V1. This formula, any formula we need to use to solve the problem for the neta. Now one more formula is there. We need to show these two values are both are same. These two rounded values are both are same. For this one what we need to show means there is a small proof is there. So V3 by V4 is equal to V2 by V1, both are same. We need to learn this one. So let me go to the proof for V3 by V3 by V4 is equal to V2 by V1. So let me check this one, V3 and V4 I am taking. This is the adiabatic process. First of all, isothermal process is done from A to B. From B to C it is going on isothermal adiabatic process, B to C. So what is this initial what is this at point B condition of this thermodynamic state? It is the P2, V2 and temperature is the T1. What is the condition state of the thermodynamic system? Here is the P3, V3 and T2. This is the condition of the thermodynamic state at point C. Will you please observe at point B and C is located on the adiabatic process condition. We can apply the adiabatic condition. So as B and C are on the adiabatic process, they are in the adiabatic process, then we can apply the adiabatic condition. We can apply adiabatic conditions. So we can apply the adiabatic conditions. What will happen? Adiabatic condition, we have the adiabatic condition. Let me write the adiabatic conditions here. PV power gamma is equal to constant adiabatic condition is there. Now TV power gamma minus 1 is equal to some condition is there. So one more condition is there, we can derive here. So now we are using, this is the condition we are using, this condition I am taking. Will you please look on this one? What does it mean? T1 V1 power gamma minus 1 is equal to T2 V2 power gamma minus 1. This is the formula. So here is the first process, first initial state. This is the final state of the system. Now apply this condition here. T1, if this one is the T1, so V1 is equal to, here is the V2 gamma minus 1 is equal to, here is the T2 is, here is the second final state is the T2 and V2 final volume of this one is equal to V2 gamma minus 1. Now I am taking what does from this equation, what we will get? T1 by T2 is equal to, now I am sending this 2 to this side, I am sending this V2 this side. So what will happen? If we send V2 this side, what will happen? Tell me. So V2 divided by I just now I written something wrong. This is the V3. Okay, thank you. So V3 divided by V2 whole to the power of gamma minus 1. Let me take, this is the equation number 1. Now apply the same procedure at the point of where the system is moving from D to A. The system is moving from D to A. So this is the process. Again this process is done. Again this process is done from D to A. This system is moving from D to A. So this is the D, this is the A. Again the D and A both are in the adiabatic compression. It is the adiabatic compression. What is the state of the system at D? It is having P4, V4 and T2. So what is the state of the system at point A? It is the P1, V1 and T1. This is the state. Apply the thermal adiabatic condition, that is equal to TV power gamma minus 1 is equal to some constant, that is equal to T1 V1 gamma minus 1 is equal to T2 V2 gamma power minus 1. So at stage 1, at stage 2, let me take this is the state 1 and state 2. Now apply this one. So here is the temperature is equal to T2, here is the volume is equal to V4, gamma minus 1 is equal, here is the temperature is equal to T1, here is the volume is equal to V1 gamma minus 1. Again our goal is to find out the T1 by T2. So send T2 this side, send V1 this side. So that is equal to T1 by T2 is equal to V4 by V1 gamma minus 1 we are getting. Let me take equation 1. Will you please look on this one? Equation 1 and equation 2, left hand side both are same, then right hand side must be constant, must be equal. So then 1 is equal to 2 only LHS, then the RHS are equalating. So RHS are equalating means what is the RHS of first equation? So RHS of first equation V3 by V2. So V3 by V2 whole to the power of gamma minus 1 is equal to second equation V4 by V1. So V4 by V4 by V1 whole to the power of gamma minus 1. Then powers are equally, they can be cancelled. Then send this, what is our goal? We need to prove V3 by V4 is equal to, that is equal to V4 send this side, V2 send this side, that is equal to V3 by V4 is equal to V2 by V1. So we prove this value. Then what will happen if we prove this one? Proved. So what will happen? Now let me go to the Carnot engine efficiency formula. So will you please look on this one? These values are equal, then these two values will be cancelled because of V3 by V4 is equal to V2 by V1. So just now we proved. So these two values will be cancelled. Then neta formula can be written like this. Neta is equal to W by Q1. This is the one formula. W1 minus W3 divided by W1. This is the another formula. R1 minus Q2 divided by Q1. One more formula. 1 minus T2 divided by T1. I have more formula. These are the very important. So then what is the conclusion from this one? What is the conclusion from this one? Very important conclusion. Again I am writing neta is equal to W by Q1, that is equal to W1 minus W1 minus W3 divided by W1, that is equal to 1 minus Q2 divided by Q1. So that is equal to 1 minus T2 minus T1. Will you please look on this one? There is no, will you please look on this one? So that means that the efficiency of the Carnot heat engine is independent of the property of the working substance. It is depending only on the temperature of this source T1 and the temperature of the sink T2. So the conclusions are here. Conclusions, very important. So that neta is independent of properties of working substance. That means they are not coming any parameter related to the working substance. So this is the first condition. Second conclusion is neta depends only on T1 and T2. T1 and T2 means T1 is the source temperature, T2 is the sink temperature. So it depends on source and sink temperature. Now one more conclusion, neta is equal to third condition, 1 minus T2 divided by T1. So T2 is the sink temperature. Sink temperature means it is at lower temperature. So neta will become 1 when T1 is equal to 0. So neta equal to 1 if T2 is equal to 0. So 0 means it is the absolute temperature, 0 Kelvin. So 0 means 0 Kelvin. So 0 Kelvin means it is the least possibility of temperature in the Kelvin scale. So 0 Kelvin reaching is really, it is a impossible condition. That's why T2 will not be, it may not equal to the 0, then neta will not be equal to 1. That is equal to neta is always lesser than to the 1. That is a very important one. So one more time repeating. So neta is equal to 1 minus T2 1 minus T2 by T1. Neta will become 1 if T2 is equal to 0, that is equal to 0 Kelvin. So 0 Kelvin is the least temperature value in the Kelvin scale. So the 0 Kelvin is an impossible reaching point in the Kelvin scale. That's why neta will never be equal to the 1. All heat engines which are working in the two different temperature, those heat heat engine efficiency will always lesser than to the 1. It is a theoretical heat engine, so that means a Carnot heat engine can be bring for 0 Kelvin because of it is not a practical heat engine. So Carnot heat engine efficiency may be equal to the 1, but all other heat engines may be equal to the all heat engines efficiency will lesser than to the 1. So neta is equal to 1 for Carnot heat engine. when theta 2 is equal to 0 Kelvin. This formula will be remaining all perfect practical heat engine, this value must be equal to the 0. Now let me go to the this heat engine neta is equal to lesser than 1 means neta formula I am writing 1 by the work done divided by heat supplied to the system. Heat supplied to the system, this is the formula we are having. So net work done, so that means what does that means? So if these values must be equal, then only neta is equal to 1. That means W net is equal to Q1, then neta is equal to 1. That means all practical heat engines are getting the neta value is equal to lesser than 1. What does that mean? That means any heat engine, it is impossible to convert the supply heat energy as a working as a work. That is a very important. So as neta is equal to lesser than for practical, that means all heat engines for all practical heat engines the supplied amount of heat may not possible to convert to work. Very important. So because of neta is always lesser than 1, so that is equal to neta is equal to W by Q1. So neta is lesser than 1, W is always lesser than to the Q1. So the supply amount of heat is large as compared to the work which is dragged from the heat engine. This is the very important question. So they may ask the questions on neta values, and also they may ask the graphs, they may ask the formulas. So I hope you understanding this lecture. I am feeling that you may feel somewhat bored in this one because of it is a lengthy concept. I should not break anywhere in this one. If you are feeling that these lectures are useful for your preparation, I am requesting you please subscribe our channel. It will be helpful for our channel also. So if you are interested to any doubts, clarification or any other class information, you can come to the WhatsApp group also. We can share our knowledge. Thank you for watching. Thank you very much.